Thanks again for the question. I'll do my best to try and deconstruct this and maybe give you a bit of an alternative here. But I've given a bit of a look. Where I'd start, I guess, is that your teacher's translated this vector equation of a line to the red text below. Firstly, I, again, just as a theory, think that it's much easier to read if you do it in column vectors. So I guess I'll do it in blue over here. So I would write the initial actual equation of a line as 1 minus t, 2 minus 3t, and then 2. Then the first translation that your teacher's done here is they basically separated out the components. And that's absolutely fine. So they've just taken, okay, well, which bits are related to the t and which aren't. And so obviously we've got just 1 here. And then there's so what we're trying to do, I guess, is separate it out into, okay, what's the position vector? And then we've got t times some directional vector. And that's what they've split it up into. So 1 is from the position vector, 2 and 2. The bottom one obviously has 0 components of t. Second from the bottom has -3 components. And then -1. So that would be, okay, well, what they've written in the red, that's how I equate that if I'm looking at this question. Now the second component I'd want to deconstruct here is, okay, this diagram. This is pretty important, but it's a little bit difficult to understand. It's kind of conceptual. So obviously you've got your origin here, and I think that's a key pickup. Because then if you're looking at any kind of line from the origin, or any point from the origin, it's always back to this point O. And so this is your point A here. And there's obviously no label, this is just a generic diagram, but that is 1, 3, 2 there. And what it's talking about is, okay, look, well, we've got the line that runs like this with a specific direction. And so depending on what the actual point of reference is and whether it is 1, 2, 2 here, or some other point along this line, and there are going to be multiple points along this line, what the constant feature is that, okay, yeah, it's got the same direction here. And so when we're looking to find a distance, what's crucial is that, and why they've got this p prime in the diagram here, is that the actual shortest distance is always going to be perpendicular to the line. What's interesting about the working here, and I think this might be where you're getting stuck a little bit, is that everything's referenced in terms of p prime. So this little p dash, you've got ap dash, op dash. And it's like, okay, well, looking at the diagram, we're actually at p and not p dash. The reason it's a p dash is because we want to assume that we're going to the point that is perpendicular and therefore represents that distance. So it doesn't matter if we just move this over, we just get a different triangle, whereby this vector here, a to p, is actually OP minus a, or in this case, O to p prime, where p prime is kind of your ideal point, minus O to a, and that's what they've done here. And because O to p is the vector equation of that line, we can then express it in terms of the numbers that we've been given. So we want to find, yeah, a to p. So a to p, and I will write it as a to p prime here, and I'll do it in a different color. So a to p prime, which is our ideal point in the line that's perpendicular, is going to equal final minus initial, so op prime minus oa, and again we have to relate everything back to the origin because that's what our vector reference is in relation to. So o to p prime is actually just rt. It's just rt in disguise. Then what we've got is our vector O to A. O to A is just 1, 3, 2, except it's the negative version of that vector. So 1, 3, 2. We can then substitute in our actual values for R, and it's probably most clean to use this expression of it here. Yeah, because then that includes everything just inside one column. So we can write that instead as 1 minus t 2 minus 3t, and 2, or minus 1, 3, 2, and we can resolve that. So obviously here we've got 1 minus 1, that's just going to leave us with negative t. 2 minus 3 is going to leave us with negative 1, and then the t part stays. And then 2 minus 2 is 0. And so if we compare that to where we're at in your teacher's working here, we're now at this component. All right, so what are we doing here now? You might recall that this is actually the proof for whether a line is perpendicular. And I think I should be more specific by what I mean with that. What we're trying to prove is that this direction vector d, which gets added on no matter where your point on the line is. So if your point is back here, it's still going to be, okay, well, RT follows this path, but then you add on the direction vector d. So you would end up getting a different resultant vector. So this is direction vector d, and that's unchanging for our original line R. What is changing is the point it passes through. And so what we need to find is, okay, at what point is this line here, A to P prime, perpendicular to D? Because at that point, or when I say point, what I mean is at that value for T, because that's our unknown here, is how long is this direction vector? Like, how much of the direction vector has to be factored into our line here for it to match up to this actual nice perpendicular state. And so that's what we're trying to solve for. So to find this perpendicular to D, we're going to use our scalar dot product. Okay, and what we're comparing here is direction vector initially, and that's why we separated it into the two components rather than just a single column vector. And we're comparing that direction vector to the actual vector A to P prime. And so we need to dot those two together. So that'll be negative 1, negative 3, 0, dotted with negative t, negative 1, 3, 0. And we have to say, okay, that's going to equal 0 because they're perpendicular. Okay, so that's going to be negative 1 times negative t, so positive t. Okay, and when we dot those together, we'll get this equation. This can be simplified a lot though, so we can say that's the same as t plus, and if we take out a negative from this bracket, it'll cancel with this negative. So we'll get that equals 0, and then we can multiply together and solve for t. So that's 10t plus 3 equals 0. Therefore, t is going to be negative 3 over 10. And okay, what does this mean? Well, what that means is that the t value here for this line, or this vector, A to P prime, which is perpendicular to our original direction vector, will give us the distance perpendicular to the original direction vector. Meaning, if we substitute in negative 3 over 10 into this actual AP vector, what we should get is just the resolution of, okay, this is the actual value of the vector. And if we do that, we can say this is AP t equals like that. So that's only going to be 3 over 10, and then negative 1 minus 3 times over 10. If we resolve that, that's 3 over 10, and then that will be 9 over 10 minus 1, so minus 10 over 10. That will be negative 1 over 10 j, and then, of course, sorry, I should have put this in before, 0k. So now what we know is that the vector AP prime is a vector with 3 over 10 units in the I direction and negative 1 over 10 units in the j direction. How does that equate to distance? Well, this is a vector quantity. If we want to just find the magnitude of that vector, you could recall that the magnitude of AP, which is in fact the distance from the point A to our line, will be the square root of the component squared. So this concept And that's where they've got, okay, 9 and 1 from. So that's just z squared. And then they've just resolved that into a nice surd. And that's pretty much the entirety of the solution. I could work through how they've gone from there to root town 10, but that's just stuff that you can do in your calculator to confirm it, or you can just work through this to finish it off, and that should make sense. But I hope that helps to kind of correlate what you're seeing with what you're understanding here. It's not perfect, like there are definitely different ways to approach it. My kind of main thing is I always love using column vectors, it just makes a lot more sense. But yeah, I think even like having a go at drawing this diagram yourself rather than using the diagram that they give you, kind of the default one, that's like, because if they give you that diagram, it's like, okay, yeah, I see, it's a diagram, cool. But if you draw it yourself, you have to kind of think about what you're doing when you draw it, and okay, well, actually, this represents like the optimal value of RT, which makes these two perpendicular. And why we need the perpendicular point is because that's in the shortest distance from the point to the line. So yeah, I think it's just about making a few connections there, and then hopefully I've explained a few things that your teacher has gone through here that you might not be able to get before. But hope that helps again, and yeah, let me know if you've got any questions.